Welcome to the Pre-Calculus Mathematics for Calculus textbook series. This lesson is written based on Chapter 3, Section 4, Part C, the upper and lower bounds theorem. In today's lesson, we're going to learn how to use the upper and lower bound theorem to find bounds for the zeros of a polynomial. And before we get started, you should know how to use Descartes' rule of signs and find all possible rational zeros using the rational zero theorem. Let's get started. So let's get warmed up with a synthetic division problem. Pause the video, restart when you're ready for the answer. I will show it in 3, 2, 1, now. Okay, hopefully you got the right answer. Also, don't forget there's a placeholder in the x squared term. Those are very important. And remember, synthetic division is huge for finding rational zeros. If you struggled with this, go back and review Chapter 3, Section 3. We have a great video on that. Now let's learn about some upper and lower bounds. Let's say that C is a zero of polynomial P. If C is between A and B, we call A the lower bound and B the upper bound. Finding the lower and upper bounds of zeros of a polynomial can be helpful for us. It's just more efficient. We start off with a lot of zeros, and this will help us make the list smaller. Why don't we take a closer look at how this works together? We can use synthetic division to find the bounds of our zeros. So let's begin with our lower bound A. For a negative number a, if we divide our polynomial by x minus a and the quotient and remainder line are alternatively positive and non-negative, then a is a lower bound. Okay, what in the world does that mean? It just means that in that quotient remainder line, we basically have alternating signs, and zero can be either positive or negative as needed. On our upper bound side, when we divide our polynomial by x minus b, we want to look at the quotient and remainder line and look for non-negative entries. Now just keep in mind, zero can satisfy that, so non-negative. Then b is an upper bound. For our first example, we need to show that the real zeros of this polynomial are between -3 and 2. So essentially, we want to prove that -3 is a lower bound and 2 is an upper bound. Pause the video and perform synthetic division using x equals -3 and x equals 2, and restart when you're ready, and we'll analyze the results together. I will show it now. Here's our synthetic division for x equals -3 and our synthetic division for x equals 2. For both, the remainder is non-zero, so these are not roots. The quotient and remainder line for x equals 3 has alternating signs. Okay, so this is a lower bound. For x equals 2, notice that we have non-negative entries in the quotient and remainder line, so this is an upper bound. So we can say that number 1, neither of them are zeros, and number 2, by the upper and lower bounds theorem, all of the zeros lie between -3 and 2. In example 2, we need to show that for a given polynomial, the zeros are greater than or equal to -4. Pause the video and give it a try on your own. Start when you're ready. I'll begin my answer now. Okay, I'm going to perform synthetic division. And I can see that my quotient and remainder line have alternating zeros. Now, I know what you're wondering. What about that zero right there? Remember, zero can be either positive or negative when needed for this theorem. So now I know that -4 is a lower bound for the real zeros of P. All done. In our third and final example, we are asked to fully factor a fifth-degree polynomial. So we begin by finding all of our possible rational roots. Now remember, that's the factors of my constant term over the factors of my leading coefficient. I have 12 possible rational roots if you take into account the plus and minus signs. So I need to have some strategies about how to approach this. Otherwise, I'm going to be testing solutions forever. Okay, so it's time to test my roots. I am going to start with x equals 1/2, but you can start elsewhere if you prefer. We'll always end up at the same place. After I perform synthetic division, which is not friendly on a math, this math is not friendly, I can see that this is absolutely not a root. And also, unfortunately, I don't get any information from that quotient line because I don't have alternating signs and I also don't have all non-negative entries. So we just have to keep trying. For my next one, I'm going to test x equals 1. So after performing synthetic division, oh my gosh, great, a remainder is 0, so this is a root. But I also want to check my quotient and remainder line to see is there any information, and there isn't. Again, no alternating signs and no completely non-negative entries. So we have 1. I'm just going to write my new polynomial that has my new factor and then my depressed equation, which is coming from my synthetic division. Next one. Next, I'm going to test x equals 3/2. After performing synthetic division, oh, good news. Again, my remainder is 0, so this is also a root. But if I look at my quotient and remainder line, guess what? There are no non-negative entries, so 3/2 is an upper bound. So I still have a couple more zeros left. I have 3 more zeros to find, but now I know I shouldn't look for anything that's greater than 3/2. Okay, I'm going to test x equals -1 next. After performing synthetic division, I can see that this is a root. Oh my gosh, I'm so lucky. It's not like I already knew the answers. Anyway, and also note that my quotient and my remainder all have non-negative entries. So there is an application of the upper and lower bounds theorem, but that's okay because guess what? When I write out my depressed equation, it's a quadratic equation, so we know how to solve this for sure. So now we're going to stop with our synthetic division, and now we're just going to break down this remaining polynomial by hand. Okay, so now I'm excited. We can finish with factoring. Here's our current polynomial. 2x squared plus 8x plus 6, I can factor a 2 out of that. Then I'm going to factor x squared plus 4x plus 3 again to get x plus 1 times x plus 3. I move my 2 to the front. And we are fully factored with 5 roots. Whew. Now keep in mind that x equals -1 is a double root. That's going to happen, especially once you get into the higher degree polynomials. Great job today. Hopefully you feel good about the upper and lower bounds of a polynomial 0. And now to end, is this statement true or false? If a is an upper bound for the real zeros of the polynomial p, then -a is necessarily a lower bound for the real zeros of p. Talk amongst yourselves and I'll see you in the next one.